All right, so we're talking about this squeeze theorem. Let me just make sure this looks good. Okay. And what the squeeze theorem talks about, again, it's kind of a cool little theorem. It says if you have an h of x which is less than an f of x which is less than a g of x. So like the h of x is going to be the below or the smaller function. The g of x is going to be the bigger one, and f of x is the one that's in the middle. The f of x one is basically going to be squeezed between the two. Okay. For all x in an open interval containing c, except for possibly at c itself. And if the limit of this small function as x is approaching c is equal to some L, and that same limit is for the big function as x is approaching c, then obviously, because your f of x is between both h and g, it's right in the middle of those two, and if h and g both have the same limit there, then obviously f is going to have that same limit, okay? So graphically, what am I talking about here? It's like I have some x value c, and like this is my function f of x in the middle here, right? And there's some function g of x which is bigger than it. And it kind of does something like this, okay? And then there's some other function h of x which is smaller than it. I left for a day and all my pens are gone. I had like 5 pens here yesterday and they're all gone. I know, is it my sub? And so what it's saying is that if the limit of g of x here has this limit of L, and the limit of h of x also has that same limit of L, then obviously since f of x is between the two, it gets squeezed in there, then obviously the limit of f of x at that point is equal to L as well. Okay, so that's really all that your squeeze theorem is saying. You're not going to use it very often. It's very rare that the situations appear where you're going to have to use this squeeze theorem. But let me sort of show you a couple examples where you might see it. So let's say we wanted to find the limit of f of x when f of x is equal to x squared. And so let's graph that. Here's my x squared. That's f of x. So we need to find a function above f of x on some small little interval right around 0. But that is equal to f of x at 0. And then we need to find a function below it. And so two functions that would work in this situation, let's just pretend that h of x this is the smaller one, I guess. So this is negative absolute value of x. And let's say that g of x is the positive absolute value of x. So the negative absolute value of x would just look like an upside down v, right? So this would be my h of x. And so notice it is less than it, but at 0, it has that same limit equal to 0, right? Absolute value of x is sort of greater. And what happens here is that right around here, the purple graph is actually bigger than the pink graph. The pink graph actually comes kind of like this. A parabola does not increase as quickly right at the beginning there as the absolute value does. And so right at this point in here, as x is approaching 0, the limit of h of x is 0. The limit of g of x is also 0. So therefore, because of the squeeze theorem saying that absolute value of x is bigger, negative absolute value of x is smaller around there, they're squeezing that x squared graph in between, and so therefore the limit of f of x is also equal to 0. Now, would you use the squeeze theorem to find that value? No, you would just do direct substitution for x squared, because you plug it in and you find that it's 0, right? So this is kind of like a silly example, but it does get helpful later on if you have some other ones. All right, so this is an interesting one now. This one is this function that's very strange that we would never know how to graph by hand, so we would graph this in our calculator. Oops. So it's x squared times the sine of 1 over x squared. Okay. And so if I go to, let me make sure I'm in radians, and I graph this guy, it's kind of cool. Notice how it comes in, and then like there's something happening in here, but I'm not really sure what. Yeah, there's going to be some oscillation in there, but let's go in and look very closely. I'm actually going to zoom in to see what type of oscillation. So it's kind of different from the other oscillation we saw, right? The other oscillation we saw was negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1 the whole time, okay, bouncing back and forth. This one gets progressively smaller and smaller and smaller. You see that? So it's getting closer and closer and closer here to 0. So you can probably guess that the limit there might be 0, right? But if you actually tried to plug in a 0, it wouldn't work because you'd have 1 over 0, so you'd get an error, right? You couldn't actually plug in a 0 to do it. So this is a graph that we would use a squeeze theorem. So we'd figure out what would be a good graph that would be above it, one that would be below it, and prove this using the squeeze theorem. So what I would use here, and you could really use a couple different examples. Let's just graph it here. So this is that crazy function. And again, it's getting closer and closer to 0, and then it kind of comes back out. So it's not oscillating as since the other one was, right? The other one, again, was bouncing, thank you, back and forth between negative 1 and 1. This one's getting progressively closer and closer to 0. Okay, so let's find some h of x that's lower. Why don't we do negative x squared? See how this kind of looks parabolic? So it would be something like this would be my negative x squared. And so then let's do a g of x, the bigger one, of positive x squared. So kind of see how we're squeezing it in there. So for all these very small values, right, since the limit as x approaches 0 of h of x is 0, and the limit as x approaches 0 of g of x is 0. Right? We know those by direct substitution. Therefore, the limit as x approaches 0 of f of x is also 0. So it's a way to prove certain limits that you can't find by direct substitution, that you can't really find by graphing. Now, you could find this one by numerically, probably, right? Picking small, small, small values, you could probably see where it would work. But does this kind of make sense? All that the squeeze theorem is.
What's that 3 dots?
Therefore. So those 3 dots together is a mathematical symbol saying therefore. So it's like kind of like, because this and this are true, therefore I can say that true. Cool? All right, so again, squeeze theorem, I don't think you're going to see it very often, but you never know, next year she might throw it out there and you'll be like, oh yeah, I did remember hearing about that once. All right, this next part is very important. These are 2 special trig limits that we're going to have to memorize these 2. Okay. Yesterday, you guys did like just regular trig ones that were direct substitution. So like the sine of 3 pi or the sine of whatever it was. You just direct substituted. Sines, cosine, cosecants, all those. When it's something weird though, like sine of x over x or 1 minus cosine of x over x, these are 2 that you want to memorize, and I'm going to show it to you on the graph to show you what's happening. So let's look at the first one. It's sine of x, whole thing over x, right? When I go to graph this, oh, I'm zoomed out, aren't I? Let me zoom back to normal. And this is the limit as x is approaching 0. Okay. Now, if I tried to actually do direct substitution with the 0, I would have sine of 0 over 0, right? So direct substitution is not going to help me here. Okay. If I look here and I go to my table and I try and plug in a 0, I'm going to get an error message. So there is definitely a hole there that you can't see on the graph. So what this graph looks like, just have a sort of a mental picture, is it does this sort of thing, and it comes up here and comes back down. And right at x equals 0, it's at y equals 1. There is a hole there. And so the limit as x approaches 0 of sine of x over x is always equal to 1. So you just have to memorize it. There's really no other way to figure this out. You can't rationalize a numerator. You can't find a hole. You can't simplify. You can't cancel things out. You can't factor. Right? You can't do anything to simplify it. It's just one you have to memorize. Same with this other one. The limit as x approaches 0 again of 1 minus cosine x over x. This is not equal to 1. This one is equal to 0. Let me show you the graph of this one over x. So this one does an up and down sort of thing. But again, if I did a direct substitution with a 0, I'd have a 0 in the denominator. Again, check your table. If I plug in a 0, I get that error message. And so again, there's no way to really simplify these except that knowing there is a hole there and that it is approaching 0. So again, your graph would look something like this. And there's this hole right there. Okay, so for the cosine one, it's equal to 0. For the sine one, it's equal to 1. All right, so why is this helpful? Well, because when we have something like finding the limit of tangent of x over x as x approaches 0, I try direct substitution. Always start with direct substitution. Plug it in, tangent of 0 over 0. 0 in the denominator. Can't do it. Oh, maybe I can use one of my trig functions. So let's simplify this a little bit. What is the tangent equal to? Tangent is equal to sine over cosine. Okay, hold on, we're almost there, right? So then I flip this around, so I get x times the sine of x over cosine x, right? Oh, sorry, my x is on the bottom. My bad. There's my x. I flipped that around, right? And so then what I can notice is I can split this up, and this is what you guys did a little bit yesterday, is splitting up these two, right? So the sine of x over x, I recognize that's one of my special trig limits. And so what I can do is I can sort of split this up into two limits. The limit as x approaches 0 of sine of x over x. And then I can divide it by this one, because it's being divided by cosine. The limit as x approaches 0 of cosine of x. Okay, so this is a division problem, so I can just split up my limit. Again, this is the limit in front here of this whole thing. So I can take that limit and I can split it into two. Well, this top one I know, I just memorized it, that's equal to 1. For this bottom one, I can do direct substitution. What's the limit as x approaches 0 of cosine of x? That's just cosine of 0. And what's the cosine of 0? 1. And so my answer is just 1. Okay? So you just got to look at these and figure out how you can manipulate it, how you can move it to either get it to look like this first one, sine x over x, or 1 minus cosine x over x. All right, how about this next one? It's got a 4 in there. So this is the limit involving a trig function with a number in front of it. So this is a little trickier because what we had before is we have sine x over x, not sine of 4x over x, right? And so what could we do to kind of manipulate this one here? You can do what? Yeah, I'm not going to be able to split this one up, I don't think. But what I could do is if I were to get a 4 on the bottom here, then I would have the same argument on top and the same argument on bottom. I'd have a 4x on top and a 4x on bottom. And then it would work, because it's kind of like a you substitution, okay? So if I could get the same thing on top and the same thing on bottom, that would be my goal here. Well, how could I just get a 4 on the bottom? I can't just randomly put a 4 in the bottom. You could, it'd be an illegal move. But if I want to get a 4 on the bottom, I have to multiply by a 4 on the top, because multiplying by 1 is okay, right? Now that 4 on the top is just going to go out in front. The 4 on the bottom is going to come together with that x. So what I'll have now is the limit as x approaches 0 of 4 times the sine of 4x over 4x. Makes sense? And then bing, 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 this is what we wanted. The sine of 4x over 4x. Again, think u substitution. This is just the sine of u over u. And it's just, right? That's the sine of x over x. Same thing. So that part is equal to 1. Okay? So this is kind of now splitting up, if you will. The limit as x approaches 0 of 4 times the limit as x approaches 0 of sine 4x over 4x. And I'm really showing every step here. You don't have to do all this. This is our special trig limit that we just learned. That's equal to 1. Multiply it. Well, what's the limit as x approaches 0 of 4? Just 4, right? Those are our constants. You learned about those yesterday. And so my overall answer here is 4. Kind of make sense? Just want to check my rule here. All right, this last one is a little manipulation with a trig. All right, good. I'm still recording. Okay, good. With a trig function and Pythagorean identities here on this one. Okay. All right, so how do we do this one? The limit is x is approaching 3 pi over 2. Again, if I try direct substitution, what is the sign? My issue is down here in the bottom. What's the sign of 3 pi over 2 is -1. So I'd have 1 plus -1 and get a 0. Okay? So what I want to do is manipulate this somehow, and my hint is Pythagorean identities. Okay? So what Pythagorean identity could we use here? Something, kind of something. Cosine squared is equal to...
1 minus
There we go. Yeah, okay. Where's Mao? That's taking him forever.
Yeah, they were like really inefficient.
All right, so sine squared plus cosine squared is equal to 1, right? So cosine squared, if I just move this over, we know this, right? All right, so cosine squared is 1 minus sine squared. So let's replace that. And every time you're doing this, you technically, you need to bring that limit along with you. So now this is 1 minus sine squared x. Oh, this is easy. What should I do now? Factor. I could factor.
Oh, yeah.
I could factor, right? So that's a difference of 2 squares. And I would get 1 minus sine, 1 plus sine. And on my bottom, I still had the 1 plus sine, and now it's gone. So this is still sort of a factoring way, right, to figure out where that hole is, and et cetera, et cetera. And so now I just have the limit as x is approaching 3 pi over 2 of 1 minus sine. And so, oh, okay, now I can do direct substitution. I don't have any issues with the denominator anymore. 1 minus the sine of 3 pi over 2. 1 minus -1.
2.
Answer is 2. Could always check this by graphing. But again, I would expect you to be able to use some Pythagorean identities. Now this one did not use your special trig functions at all in this example, but it could have, right? It maybe could have, after you used a Pythagorean identity, there might have been a special trig function in there that you needed to evaluate. Okay? But again, those are the two you want to have memorized before your quiz. Questions? Okay, so that's it for notes before the quiz. So now we're just practicing and reviewing all day, the rest of the day today and tomorrow or Monday, and then quiz is Tuesday, okay?